In this video, I'm going to talk a little bit about systems and also the conservation of momentum. And this is in chapter 10-4 and 10-5 of the textbook. Okay, so we've talked about systems before, but just to remind you, for a system of so a system of particles is just some number of particles, right? Not just one particle, but many particles. So for a system of particles, if you apply an external force to the system, it's going to generate an acceleration of the center of mass. So the sum of all the external forces is going to equal the total mass of your system times the acceleration of the center of mass. Now, it's important to remember that this is the acceleration of the center of mass, and in general, that's going to be different than the acceleration of the individual particles. So, the total, and another definition here, so if you have a system of particles, the total momentum of the system is just the sum of the momentum of your individual particles. So the total momentum of the system, and again, sometimes you use a capital P also for the total momentum of the system. It's just the vector sum of the individual momenta of the individual particles. Now, and again, just a little definition here. So sometimes it's useful to talk about a frame of reference that has zero momentum. So if your frame of reference has zero momentum, well, by definition, then the velocity of your center of mass is zero. Then it's called the center of mass frame. And again, one other little bit of terminology here. So sometimes you talk about a closed system. So in a closed system, the system doesn't gain or lose any mass. Okay, so now we're ready to define conservation of linear momentum. So imagine you have a system of objects. So what we know is only external forces can alter the total momentum of the system. So this leads to the law of conservation of linear momentum, which says when the net external force on a system of particles is zero, the total momentum of the system is conserved or doesn't change. And it's easy to see from how we've written Newton's second law, right? So the sum of all the external forces, so the total external force, well, we know we had a version of Newton's second law that said that was just equal to the rate of change of the total momentum of the system, dp dt. And well, if the total external force is zero, then the rate of change of the momentum is zero. And the rate of change is zero, then the momentum isn't changing. So it's conserved. So another way to phrase this is that the total momentum of an isolated system of objects remains constant. And again, isolated systems are systems where the net external force is zero.